Hello, let's study how web crawler use breadth first search to find the contents we want by crawling through the internet. And if we examine a web page is represented by a URL, and inside that web page we have many URLs linked to somewhere else. For example, we can link here, and this web page have many URLs linked to other places. Of course, there could have links back to the original web page. And if we model the web pages linked by the URL, they are actually a diagram. So a diagram is another vertexes linked by edges with directions. So in this case, each vertex is a web page, and those links are actually URLs pointing from one page to another. If we want to search strings in web pages, all we have to do is visit all those vertexes, and on each page we search our string. And this is exactly what a web crawler does. Is a web crawler from a starting page reach to another page and exhausted all the links. Get a better one. I start from here. It goes through all the URLs adjacent to the current page, and then it from the page it go to another page, and it's just traverses the internet that way. And one of the common crawling algorithm is called breadth first search. What that means is from the starting page, it goes through the closest adjacent page. Once it exhausted that list, it go one step further, examine the adjacent page with distance 2. And once finish all the distance 2 web pages, it go to the distance 3 web pages, so on and so forth. So the code is like this. We create a queue, and we mark what web pages we already visited. And optionally, we can remember the distance to the new page, and this is our first web page added to the queue. As long as the queue is not empty, we dequeue the vertexes, and we find the adjacent vertexes. If we haven't visited, we visit it and start to process. The process could be anything. Here in this code, it remembers the path to it. It remembers the distance from the original to this node, and once it stops processing, it marks the page as visited. This page or vertex is also added to the queue because there are unprocessed URLs contained in this page, and and once we finish processing the nodes at the current distance, we will processing the URLs contained in this page, which is further away from the origin. So that's a breadth first search. As we look at the structure, this queue is could be handled by multiple threads. So we can have multiple threads enqueue and dequeue and processing, so the program is running faster. Here is a program use multi-threading to speed up the breadth first web crawling. And our goal is search this strange string in the xyzcode.com domain. We don't want to look any URLs pointing outside. We just searching inside xyzcode.com. And the start page is this one. So we keep a track of visited pages, and once we found the hit, we store it, and we also store the count of the hit. And of course, we could run into a problem like server return 500 error, the loading timeout. So those parameters are for edge conditions. And I didn't mention this one. This one is our web crawler cannot run forever. So if it run for a while later, we want to assume, and this is the point to assume the crawling. And the main method, we create an instance of a web crawler. The web crawler have an abstract method which to be overridden, and it's basically the a map equivalent API of the adjacent to. You give me a vertex, I give you the adjacent vertexes. So let's take a look at how the implementation goes. It's equivalent to this method, graph method. Give me a URL, and I get the string, input string, and which is a HTML code for the web page. I go through line by line and I search my string. If I find it, I add the URL into the found and increase the count. And I also parse out all the URL in this web page with the helper function. And once I found it, I add it to the URL and return it. So basically equivalent to give me a vertex, return me the adjacent vertexes. So let's get container. I'm going to get a container URLs. Once we have the crawler, we start the thread and wait for a while and stop it. Now we have the result, and we can know how many URLs we just visited and the occurrence of the search string, and which page contains that string. And so let's run the program. Run as Java application. For 1 second, it finds 7 occurrences in the HTML code of this web page. Let it run longer, it might find more hits. So 5 seconds. And okay, it crawled 200 pages and got 11 hits in 3 web pages. If you right-click, go to the page, right-click, and check the HTML code, you can count the occurrence of the string. They should add up to 11. And how the code works. So here is the start. The start actually initializes a new cached thread pool. So at the backend, our engine is still an executor framework. And we keep submitting tasks to the executor, the cached thread pool. And so this is what it does. After delay, a new crawl task is submitted. So a worker thread can start to execute the run method of this crawl task. The crawl task implements runnable. And the run method, it looks like this. It's basically the breadth first search. If you didn't visit the page, then you start processing it. I give you the starting vertex. You parse out the adjacent vertexes. Then you enqueue. Okay. Here we mentioned queue. So where is this queue? The code didn't include any queue in the declaration. Actually, the queue is implicit instead of explicit. We have the executor framework. Whenever we execute a new crawl task, this task is enqueued into an internal task queue maintained by the executor framework. Once the task is submitted, there are worker thread constantly checking the queue. If the worker thread is available and there's task available, the worker thread will dequeue the task queue and start to run it. So the enqueue and dequeue is handled implicitly. The code didn't tell the executor framework how to do it, and it's handled under the hood. So let's take a closer look of this crawl task. And this is a runnable. And this code is there because sometimes the process didn't success. The list returns nothing. And in that case, we want to unlock a page. And so later, another thread can process it again. And here we have a few comments. The run method have a few shared variables. For example, the problem. This one is concurrent map because this object is shared by multiple threads. It have to be concurrent. However, there is an important comment about the crawl task. The crawl task is actually each crawl task is only handled by one worker thread. At any time, when a worker thread claimed a crawl task, it is handled just by that worker thread. Another worker thread will not handle it anymore. So at any time, this crawl task is only handled by one worker thread. So in theory, this state is not shared. This is an important comment here. And here, the scene removed. This is atomic action, and this one is also atomic. As we see, this thread, this object is only handled by one worker thread. So when it check, after it check it's true, only this current worker thread can unlock it. No other worker thread can unlock this URL. So even though this whole state is not atomic, we don't worry about the race condition because at any time this object is only handled by one thread. Only this current worker thread can unlock it. So we are fine here. More about the executor, why we wrap the executor. So the start method, we have initialized a new cached thread pool. The reason we wrap this new cached thread pool is because we don't like the shutdown policy. The default behavior of shutdown now is it returns the tasks which is submitted but not started. However, for those tasks in the middle of the executing, the executor framework just throw it away. Don't care about those threads. So that's kind of a bug for the executor framework. In that case, we want to save those unfinished tasks, and so later we can assume those tasks. That's the only reason we wrap the executor default new cached thread pool. And those are the wrapping code. It's not very interesting. So one more things I want to point out is why we mark the tracker executor as volatile. Because if you see the exec method, it's actually shared by multiple worker thread. If you see, we call the exec and we submit crawl tasks. Once we submit the crawl task, exec create a new crawl task. Inside the crawl task's run method, the submit crawl task is called recursively. So that means another worker thread need to access this exec object, and that worker thread will submit another task, and another task is runnable will be accessed by another worker thread, which need to access the exec method. So as you see, the exec object is shared by multiple worker thread, so it have to be um, thread safe. We need to have the initialization safety. That's why we have I have marked this field as volatile. So when the worker thread start to access this object, it's already it is visible immediately. It won't see stale state where it is still initializing. And that's pretty much how the code does. One common misunderstanding is for the runnable, any code in the runnable, we have to mark them as synchronized. That is not a good practice because marked method as synchronized will potentially create a deadlock. We want to avoid a synchronized keyword. We only worry about those shared objects in the heap. For the local variables in the stack, we don't worry about them because inherently they are thread confined. For any object only handled by one thread, we don't worry about the race condition. So it depends. We don't always mark any method inside the runnable as synchronized, which is dangerous for deadlock. So that's pretty much how the program works.